All right, day 74. Today, we're tackling a really clever idea at the heart of modern AI models, positional encoding. So let's start with a really basic question. We all know word order matters to us, but does it actually matter to a machine? Take a look at this. Alan walks dog versus dog walks Alan. Same exact words, right? But the meaning is completely different. One is, well, pretty normal. The other one? That's probably making the news. And here's the catch. Without a built-in sense of order, a transformer model just sees these two sentences as a jumble, a bag of words. It knows the words are there, but it has no clue about their sequence.
So by the end of this, you're going to understand the really elegant trick models use to learn the position of every single word.
Let's dig into why this is even a problem to begin with. You see, older models, things like RNNs, read a sentence one word at a time in order, kind of like we do. It was slow, but it knew the sequence. Transformers, on the other hand, are built for speed. They look at all the words at the exact same time. It's a huge performance win, but it creates this blind spot. The model loses all that natural sequence information. It's like having all the puzzle pieces, but no picture on the box to know how they fit together. So, if the model is naturally order blind, what do we do? Well, we have to give it a hint. We inject a signal that tells it where each word is in the sentence. And the core idea is actually pretty simple. Think of it like this. We give each word a unique GPS coordinate.
Here's how that happens. Step 1, we start with the word's meaning, its word embedding. Step 2, we generate a brand new vector that only represents its position. 3, we literally just add those two vectors together. And the result? A new, richer vector that knows both what the word is and where it is.
Okay, so how do we actually create these GPS coordinates for every single position? This is where things get really clever. The classic approach is called sinusoidal positional encoding. And instead of forcing the model to learn positions, which would be slow, we just calculate them. It uses a really neat trick with good old sine and cosine waves of different frequencies to create a unique vector for every position. The beauty is, it's fixed and totally predictable. Now, why sine and cosine waves? Well, think about binary counting for a second. The first bit flips constantly, 0, 1, 0, 1. The next bit flips half as often. The next, half as often as that. These waves work the same way. Across the vector's dimensions, some waves oscillate really fast, and others oscillate really, really slowly. That combination creates a totally unique fingerprint for each position. And you can actually see it right here. If we look at a simple example with just 4 dimensions, you can see how the vector for position 0 is totally different from position 1, which is different from 2, and so on. Each one has its own unique numerical signature, all thanks to that mix of fast and slow waves.
Okay, that's the how. But why does this matter in the real world?
Well, for anyone working with these models, this is absolutely crucial. First off, it's in everything. BERT, GPT, you name it, they all rely on this. Second, it's what allows transformers to be so fast. Because the positions are just calculated, the model can still process everything in parallel. And finally, this is what lets models do things where order is everything, like translating sentences or generating code.
So when you boil it all down, positional encoding is the simple but powerful trick that brings a sense of order to the otherwise parallel world of transformers.
And the one thing to remember is this. Positional encoding works by injecting a unique, predictable signal about sequence order directly into a word's meaning.
And that leaves us with a pretty cool thought, right? Isn't it fascinating that the simple, predictable rhythm of sine waves provides the very foundation for understanding something as complex as human language?